Here we begin the coverage of continuous probability distributions. Specifically, we're going to cover the normal distribution. The coverage of Chapter 6 will be broken up into two parts. The first portion will be just an introduction to the normal distribution. And then the second portion, we're going to look at a problem and we're going to talk about how to use the normal distribution. Now this slide shows the graphs for three different types of continuous probability distributions, and you can see that there's a pretty good difference in the shapes of these things. The uniform distribution, the normal distribution, the exponential distribution, the shapes aren't alike at all, but they do have things in common. When you look at the area that's shaded in each one of these curves, that represents the probability, and the probability is always going to be 1. When you add up all the probabilities, they always have to add up to 1. So the area that's under these curves, the shaded spot, is always going to be 1. The normal is nice and symmetric, the uniform is nice and symmetric, but the exponential is skewed to the right. Now when you have a continuous variable, you can assume any value that's in an interval. You can always keep subdividing it finer and finer and finer. But what you can't do is talk about the probability for a particular value. A point has no width, so there's no probability associated with a point. You have to have an interval in order to have a positive probability with a continuous probability distribution. In some ways, that makes these easier to deal with than you do with the discrete. If you take an example of a discrete distribution, it's different to say the probability that the variable is smaller than a particular value than it is to say less than or equal. But in a continuous probability situation, the probability that you're less than or equal to a particular value is the same thing as being strictly less than. The probability of being greater than or equal to a particular value is the same thing as the probability of being strictly greater than, because there's no probability at a point. But you have to have an interval in order to have a positive probability. Each one of these probability distributions is illustrating finding the probability between x1 and x2. x2 is larger than x1, so there's an interval between those 2 points. The normal distribution is probably the most widely used probability distribution of all of them. It's used in many different places in statistical inference. There are so many different things that are approximately normal. The examples given here are the heights of people, rainfall amounts, test scores, scientific measurements. IQ scores was one of the places where they gave the name to the bell curve. Now this is the formula for the normal probability density function, but if you listen really closely, you might be able to hear the bell curve. It's a mathematical entity. There's not really anything in the world of which I know that's perfectly normal. But the thing about it is there are so many different things that are approximately normal. So it becomes really important as a probability distribution because there's so many things that it describes. There's not just one normal distribution. There's an entire family of normal distributions. Each one is defined by 2 numbers, the mean and the standard deviation. So you can have many different normal distributions that actually have the same point in the middle. They're located centrally the same way, but they can have different variability measures, different values for the standard deviation. Now if you had something that was perfectly normal, then the point in the middle would be the mean. It would also be the median, and it would also be the mode. But the normal is a family of distributions. The mean can be located at different places. You can have a negative value for the mean, which the curve in red shows that. The point in the middle is a -10. You can have 0 for the mean. The blue curve shows that possibility. But you could also have a positive number for the mean, and the green curve shows that possibility. Now in each case, these curves are pretty much scattered out the same way. So whatever the standard deviation is, it's the same for all three of them. But you can have curves that have the same mean, but they have different standard deviation values. They're spread out differently. And this illustration shows the same mean for the two curves, but the one with a standard deviation of 25 is flatter. Both of them, the area that's under the curve is equal to 1. But in order to get that area closer together with respect to the mean, the curve has to be taller. So the one with the standard deviation of 15, they're packed in more tightly against the mean. So the curve has to go up higher in order to get that area of 1. Now regardless of what that standard deviation value is, no matter how tightly packed they are against the mean or how far they're spread out, it's always going to be true that half of the area under the curve is to the left of the mean and half of it's to the right of the mean. So the probability that you get a value that's larger than the mean is 0.5. The probability that you get a value smaller than the mean is 0.5. Now this is a continuous distribution, so the probability that you have a value that is exactly equal to the mean is 0. You have to have an interval in order to have a positive probability. Now with respect to the mean, most of the values are close to the mean. If you go one standard deviation above and below the mean, that interval between mu minus sigma and mu plus sigma is going to contain 68.26% of all the values in that particular normal distribution. If you go out 2 standard deviation units from the mean, if you look at the interval from mu minus 2 sigma to mu plus 2 sigma, you're going to have a little over 95% of the values in that normal distribution. If you go out 3 standard deviation units on each side of the mean, you're going to pick up virtually all of it, 99.72%. This is referred to as the empirical rule. Now this graph illustrates the empirical rule. Now let me just make up some numbers here. Let's say that the grades on a test were normally distributed and that there was a mean of 80 and there was a standard deviation of 6. One standard deviation unit below the mean would be 80 minus 6, which would be 74. And then 80 plus 6 would be 86. So the number of values in terms of a percentage that you'd expect to be between 74 and 86 would be 68.26%, assuming that they're normally distributed. Now if you go out 2 standard deviation units, 80 plus 2 times 6 would be 92. 80 minus 2 times 6, 80 minus 12 would be 68. So you would expect roughly 95% of the scores to be between 68 and 92 if they were normally distributed. And then the third value in the empirical rule is for 3 standard deviation units. Now 3 standard deviation units, assuming that sigma is equal to 6, let's see, 6 times 3 would be 18. You add that to 80, you'd get 98. We subtract that from 80 and we come up with a 62. So we would expect almost all of the scores, 99.72% of the scores, to be between 62 and 98. Now, by changing the value of the mean and changing the value of the standard deviation, you can get any number of different normal distributions. But there's one special one. With a mean of 0 and a standard deviation of 1, that normal distribution is called the standard normal distribution. Now, commonly, people take the standard normal distribution and they figure out what the probabilities are for this case, and they'll put that information into a table. Now, there are different formats for that particular table, but it's called the z-table. There's a really simple formula that lets you convert any normal distribution to the standard. And then once you get the standard value, you can use what's called a z-table, and you can figure out what the probability values are. Now, to get the z-value, the standard normal value, you take the difference between the x value, that's normal, and its mean, which is mu, and take that difference and divide it by sigma, which is the standard deviation. Now, what that number represents is how many standard deviation units x is away from the mean. If it's positive, x is above the mean. If it's negative, x is below the mean. But the probability from the mean is going to be the same. It doesn't matter whether it's positive or negative. Now, here's two formulas that are available in Excel for dealing with the standard normal probability distribution. There are other functions in Excel for dealing with normal distributions, but the ones with the .s in the middle are for the standard normal. Now, the norm.s.dist, you provide as an argument the value of z, and it's going to figure out what the probability is that's less than or equal to that z value. The inverse, the .inv form, it works the other way around. You provide the function with an argument that is the probability that's less than or equal to some z value, and this function will figure out what that z value is. But sometimes you want one form and sometimes you want the other. Now, what I recommend that you do is to draw a little picture of a normal curve when you're working out probability problems like this. Just draw a little illustration of what the curve looks like. This is for the standard normal variable for z. So 0 is going to be in the middle of that normal curve. 1 is going to be to the right. Now, if we want to have the probability that z is less than or equal to 1, that's going to have to get to 0 and then pick up the 0.5 that's on the other side of 0. So the answer is going to be a number that's bigger than 0.5. But you can get Excel to figure that out for you. You can just type in equal norm.s.dist and inside parentheses put 1. Excel will calculate what is the probability that you would get a z value that's less than or equal to 1, and it would just put that answer inside that cell. Now, the one that's in A4, we're trying to get the probability that's between 0 and 1. Well, the function that's in Excel works to the left. It's less than or equal to. So we can take the probability that's less than or equal to 1 and then take off the part that's less than or equal to 0, which that's going to be 0.5. The one that's in A5, we're getting the probability that it's between 0 and 1.25, that the z value is somewhere in that range. So you take the probability that it's less than or equal to 1.25 and then take off the part that's less than or equal to 0. And that'll give you the part that's in that range. But if you draw the picture, you can see it. The one that's in A6, we want the probability between minus 1 and plus 1. We'll just find the probability that's less than or equal to 1 and subtract the part that's less than or equal to minus 1. In A7, we're looking at the other side. We want the probability that z is greater than or equal to 1.58. So you take the probability that's smaller or equal to 1.58 and subtract it from 1, because your probabilities have to add up to 1. If you want the probability that's less than or equal to a value, just put that value inside that normal distribution function, and it's going to return the probability for you. Now when you get your answer, if you look at the picture, see if that answer is reasonable. Being less than or equal to 1, 1 is to the right of the mean of 0. So being bigger than 0.5 makes sense. If I want the part that's between 0 and 1, I should get a number that's less than 0.5. 0 to 1.25, that ought to be a little bit bigger than it is from 0 to 1. Now when you're going from one side to the other side, you can get an answer that's bigger than 0.5. Now if I want to get the probability that's greater than or equal to 1.58, 1.58 is to the right of the mean. So if I'm going to the right of 1.58, I've got to get a number that's smaller than 0.5. Likewise, on the one in A8, less than or equal to a negative 0.5, I should get a number that's less than 50%. Now the inverse function works in the opposite direction. What you do is you provide the inverse function with the probability, and it's going to return the z value that corresponds to that probability. The one in number 3, in the A, we want the z value where there's 10% in the upper tail. Well, when you apply it to the function, you need what's on the left side. 10% is on the right side of this point. There's going to be 90% on the left side of this point. So you feed the 90% value, the 0.9, into the function, and then that's going to return the z value. Now in 4a, it says we want the z value where there's 2.5% in the upper tail. Well, if there's 2.5% in the upper tail, the function works on the lower tail. There's 0.975 in the lower tail. So feed that into the function, and that's going to get you the z value. Now number 5, it's built for the function. You want the z value where there's 2.5% in the lower tail. Well, that's what the function needs. What's in the lower tail? What's on the left-hand side? What's less than or equal to? So you put that 0.025 into the function, and it'll give you the z value. I think it's helpful when you're looking at problems of this nature to check to see whether or not your answer is reasonable, is to just draw a picture of it. If you draw a picture of that standard normal curve with 10% in the upper tail, look to see whether or not that 1.28, does that seem reasonable? Compare it to the numbers that you'd expect based upon that empirical rule. The z value with 0.025 in the upper tail. Well, if there's 2.5% in the upper tail, then there would be 2.5% in the lower tail, the same distance. And that means there'd be 5% in the tails, there'd be 95% in the middle. And that's that second level on the empirical rule. So there ought to be about 95% that corresponds to 2, and we're coming up with plus 1.96 and minus 1.96. Those are reasonable answers. Now this concludes the introduction to the normal distribution. The next presentation, we're going to get into actually solving problems using the normal. And I really encourage you to draw a little picture. If you look at the picture, it's going to help you to see whether or not your answer, whether or not it's reasonable.